Welcome to this tutorial on a well service for ongoing maintenance, or AWSOM. This tutorial discusses the why of AWSOM. What's next? The computer. Arduino Mini Pro. Where is the computer? It is that thing there. This is a wonderful machine. Little blue device there. Wonderful. I've never used Arduinos before this project. I've never programmed them before. But when the first unit came in the post, I opened the package, and from nothing, I hadn't even got any of the software, within an hour I had it blinking a light, flashing a light. I know it doesn't sound much, flashing a light, but it was a fantastic device.
A couple of things you should be wary about and take note of. Firstly, it should be an Arduino Mini Pro, not an Arduino Nano. The Nano has the USB circuitry on, which takes more power, so use the search term in the circuit diagram for the Arduino Mini Pro.
These are 10 times more expensive in Europe than out from China. If the computer is purchased from a non-European source, it is highly likely that it will have to be programmed via the IDE as an Arduino Nano, not the Mini Pro. It took me 3 months to figure that out. So just remember, just go through them and try them, which programs it. Check the programming pin out, as the pin order can change between suppliers. What do I mean by that? Those pins there, which program this little device, those pins there, on this device, it's receive, transmit, ground, VCC, and then ground. But on another device, oh here we are, another device, they're the other way around. It's so you've got to be careful when you're programming it. Just watch. But otherwise, they are fantastic little devices. Yes, we talked about programming it, Mini Pro or the Nano. Check the programming pins. Make sure the AWSOM ID is incorporated in the text message. It must be different for each computer. You can't rely on the telephone number, which we found. So unfortunately, it means the program for each Arduino is going to be different. Ensure the Arduino VCC voltage matches the serial programming voltage. Once again, it took me some time to realize this. If the battery voltages here are slightly low or too high, then the Arduino makes it very difficult to program. So make sure the battery voltage matches the programming voltages. Oh yes, next thing, to save power, these little computers have an LED. They have to be removed before you use them. It takes too much power otherwise. I would strongly suggest you program the computer prior to plugging it into the board, because once you plug it in or start using it, it can be difficult to remove. Ensure the conformal coating does not cover the connecting pins. That's these pins here. Cover the top, not the reset button, but the top unit there. The Arduino is very tolerant for mistakes, user mistakes. And the calibration of temperature and voltage is not essential. Oh yes, this is the thermistor, which has to be calibrated for each device in the software. It should be. It doesn't really matter. You're not. It's just pumping water. We're not really doing a scientific analysis on the temperature. It'll be a couple of degrees out, but does it matter? No. So it doesn't have to be calibrated. The voltage uses 200k resistors to divide the voltage by 2, so the Arduino computer can read it. Now, when the voltage is higher than 5 volts, when the battery voltage is higher than 5 volts, then you need a different library. You need to read it to when it's lower than 5 volts. There's an internal band gap reference diode, 1.1 volts, and sometimes it references that, and then it switches when it's when that is no longer applicable. That switchover can be a little bit difficult at around 4.8 volts. Right, that is that. So the calibration of the temperature and voltage is not essential. It's nice, but not essential. Right, what's next? Battery voltage charger and the power switch. So this comes in 3 places. The power switch is here, the battery voltage charging mechanism is here, and that's the battery there. So you've got 3 little blocks here. Where are they? There they are. You've got the batteries, the big long batteries here. You've got the little charging mechanism here. Also the software looks after the charging. And there's the power switch, and that's the plug-in for the battery as well. Use the same plug for both. Make sure the different components count is kept the same. We've used that philosophy in a couple of other places as well. We'll come on to that in a minute. Right, lessons learned from this little thing here. We're using nickel metal hydride batteries, not lithium. Why do we use nickel metal hydride? Because they're safe and robust. They're really great, and they can go down to 0 volts from very tolerant, whereas lithium, whole new different regime. They're 4 ampere hour batteries to make sure it will last and give consistent power over the period, over the 4 weeks or slightly longer. The circuit diagram, we used 2 Schottky diodes. Let me quickly go back to that. Only need 1 Schottky diode necessary to protect from overvoltage from the solar cells and protects from polarity reversal. What do we mean by that? Well, in the circuit diagram here, I've got 2 Schottky diodes from the solar cells coming in there to reduce the voltage, going through there to charge the batteries. Didn't know how much voltage the Tanzanian sun would produce, so just in case it produced too many volts, I put a second Schottky diode in there with a shorting link, so if the batteries, I could see the batteries being charged up too much all the time, that could be a selectron test, a shorting link, so it could be cut and reduce the voltage. That's not necessary. Just a 1 volt drop is fine, and so we can save a component and take that out. Keep the copper tracks as far apart as possible to avoid possible corrosion. I don't mean copper tracks, I do mean copper tracks, but the power lines, the positive and negative, I put them straight next to each other, kind of a power, which is not a good idea. They should be a bit separated a bit. Ensure conformal coating does not cover the plugs or sockets. The conformal coating cannot be what I used, which was the acrylic form. I strongly recommend we used thin 2-part epoxy. In fact, the same stuff for retains the photocells on the case. And do both sides of the board, this side and this side, because the water goes through the holes and attacks the copper from behind the conformal coating here. Also, this acrylic conformal coating, which was coated, cracks with vibration and temperature cycling. It cracks off, and of course that shows the copper, which is disastrous. Talking of component counts, the shock diode across the relay coil, I've used that. So there's the relay coil. I've used the same diode, the Schottky diode. It's not ideal, it's not perfect, and it does stress certain components, but once again, to keep the component count, the different component count down, the same diode, which is fine, and we haven't had any problem with that at all. And the calibration of voltage is preferred but not essential, as default settings cope. Right, that is the lessons identified for the battery charger, and power switch. Oh, the charging circuit. When the charger does go too high, then this little computer detects the high voltage, and it switches that switch and stops charging the battery for half an hour. In addition to stopping charging the battery, it makes that switch, the same relay, turns that switch on, which powers this up and powers this up, which takes another 100 milliamps for half an hour or so, which kind of keeps everything controlled. That relay does two jobs. It keeps the battery from overcharging, and it also, at night time, it turns the texting module on through that regulator. Now we come to the texting PSU. This PSU is that unit there. Where is that little unit? It's adjusted to 4.1 volts to make sure the power supply, it supplies power to the module there. That's the module. Now, this is key. These two modules are regulators. They look similar. One causes disaster and one doesn't. The main difference is this can be fed with an input of down to 3 volts. 3 volts on the input side here, and you can twiddle that to get 4.1 volts out of here. Perfect. This one, on the other hand, it needs a minimum of 3.8 volts to twiddle that to 4.1 volts to get out. So no matter what you put on here, from 3 to 15 volts, you still get 4.1 volts out of here. Lovely. This one, as soon as you start to go below 3.8 volts, it self-oscillates, takes huge amounts of current, and this voltage goes up to 35 volts. And guess what happens then? It pops the SIM unit. Right, lessons learned from there. Use the right regulator, very important. Search eBay for that search term. Buck boost voltage converter, 3 to 35 volts, 1.25 to 35 volts output. Input voltage from 3 volts, not 3.8, and check output can be set to 4.1. So it's something I can't get from my normal supplier, but there's plenty on eBay. Strongly suggest you adjust the voltage prior to installation, so make sure that that little unit is twiddled to give 4.1 volts out of here before you put it in the circuit and turn it on. Suggest you put in a resettable polyfuse. Where is the fuse? It's there. That's the fuse. So when the relay turns power on, it goes through a fuse, so that limits the current. So anything funny happening here, the little fuse will blow and then reset itself. If you need to do vertical fixing, make sure it's secure, and I would suggest ensure the two-part epoxy conformal coating is used to assist in that process, because it's under temperature cycling and of course vibration 18 hours a day. Right, that's lessons learned for the texting voltage regulator. Now we come on to the last thing you might be pleased to know, which is the texting module itself.